Okay. So let's get back to work. Back to work. Back to work. Okay. So here's the basic comparison test, right? It says that if you have, if you have two sequences, and one of them is bigger than the other, right? You have two non-negative sequences and one is bigger than the other, then the sum of if the sum of the big guy converges, then the sum of the little guy converges too. Okay, and the reason for this is just why does it why? Well, just consider the sequences of partial sums. Okay, think about the partial sum sequences. Okay, so let's say that let T sub n be the partial sum sequence for the big guy, and let S sub n be the partial sum sequence for the small guy. Okay, so you think, well, if summation b sub n converges, that happens if and only if the T sub n are bounded. Right? If the T sub n is a bounded sequence, Okay. Okay, but if that happens, then what do you know, right? If T sub n is a bounded sequence, then what does that give you? Remember, the A sub n's are smaller than the B sub n's. So what's the relation between S sub n and T sub n? Yeah, the S sub n's are smaller than the T sub n's, right? The partial sums of the smaller guys are going to be smaller than the partial sums of the bigger guys, right? Well, if the T sub n is a bounded sequence, then what do you know? Somebody say it, please. S sub n is a bounded sequence, right? If the T sub n's are bounded, certainly S sub n is a bounded sequence. Right? Well, if the S sub n is a bounded sequence, then what happens? Then it converges, right? If that happens, then summation A sub n converges. So it's pretty straightforward, right? If the B sub n converges, that's the same thing as saying that the T sub n is bounded, right? Well, if the T sub n is bounded, then that makes S sub n also bounded, right? And if S sub n is bounded, then then this converges. Then the summation A sub n converges. Okay. And I'll let you think about the second one. The second one basically the same sort of argument. Okay, so I'll leave the second one. So this is the explanation for 1. You can do the explanation for 2. You can either use 1. Actually, 1 implies 2, or actually 1 is equivalent to 2. Or you can do it using this sort of argument. So I'll let you think about it. Right. Right. Actually, maybe we should just do it. Right. Okay. So actually, this is maybe useful for you. A implies B. So in logic, A implies B is the same thing to saying that not B implies not A. Not B implies not A. If this is the statement, then this is called the Contra Position. For example, if I say, if you are Chinese, then what? You have black hair, okay? And you have black hair. Okay. That's the same statement as saying, if you do not have black hair, if you do not have black hair, then you are not Chinese. Right? You see that these are basically the same statements, right? If you're Chinese, you have black hair. If you do not have black hair, then you're not Chinese. Right? It's exactly the same statement, just worded backwards. I mean, it's not true. I mean, not all Chinese have black hair. There are Chinese people who have no hair, or there are Chinese people. I saw an albino the other day, right? Somebody who has no color in his body, and he had white hair, right? And there are Chinese albinos. Anyway, so you know what I'm saying here, right? Well, let me say it this way. This is definitely true. Then, if you are Chinese, then you are a human being. This is easy. Okay. If you are not a human being, then you are not Chinese, right? So to make it more straightforward. Okay. Right. These are the same statements. Okay. This is the direct statement. This is the contrapositive statement. Okay, and so what you notice is that actually this statement is the contrapositive of that statement, right? Bn converges, then An converges is the same thing. Is exactly the same thing as saying that if An diverges, then Bn diverges, right? So in fact, we don't even need to say this second statement. It's the same thing as the first statement. Okay, so that's the basic comparison test. I hope it makes sense to you. Okay. Okay. So now comes a very interesting test called the limit comparison test. So again, you have A sub n, B sub n. This time they are positive series. Okay, so A sub n and B sub n are bigger than 0. They're not just non-negative, but they're in fact positive. So now, if the limit of the ratio of corresponding terms is some number bigger than 0, then A sub n converges if and only if A sub n converges. Okay, this is a pretty cool test because it really is sort of like it captures your intuition about series. So let me give an example. Earlier we did this one, root k plus 1, right? And we said, you know, what this really is it should be something like root 1 over k, 1 over root k, right? That one really shouldn't matter that much, okay? And what the limit comparison test says is that we can make that comparison. You say, okay, you say, well, 1 over root k plus 1 over 1 over root k is root k over root k plus 1, right? And you take the limit of root k over root k plus 1 as k goes to infinity is 1, right? Right? So, limit comparison says that this converges if and only if this other guy converges. Okay. So it's saying that, you know, it allows you to say that these guys are basically the same, right? Because if you look at the ratio, the limit of the ratio, you get a number. You get a constant number. So that means that the behavior is going to be the same. Okay. Okay. Let me explain why first. So why? And then I'll let you try some. Okay. So why? So if the limit of the ratio is some number, right? Well, here's the idea, right? The idea is that then A sub k is basically L times B sub k, eventually, right? A sub k is basic, you know, for huge k, A sub k is basically L times B sub k, so A sub A converges if and only if B sub A converges, B sub k converges. Right. That's the idea. Right. You know, if the limit is L, you know, then basically A sub k is going to be L times B sub k. Okay, but let's make that, we have to make that a little bit more proper. So you say, if this is equal to k, then they exist at n such that if k is bigger than n, ak over bk minus L is smaller than, say, L over 2. Does that make sense, right? Remember what, you know, if the limit is something, then we can make the terms close to L, right? Right? We can make the terms as close to L as we want. We're going to make them L over 2 close. maybe take a minute and talk to each other. I think and see if you can answer. Again, see if you can come up with some question or clarify any questions. So this is, make sure that you understand this step here. Okay, just talk to each other for a minute, please. Just like, does it make sense? Yes, no. Okay, right, so here's the picture. Here's the picture saying, if we're looking, this is L, right? And let's say that here's L plus 3, L plus, this is 3/2 L, and this is 1/2 L. Okay? We know that we can make, there's some time, and past that time, all the AK over BK lie between these two lines, right? We can make them all close to L. We can make them all within 1/2 of L. Okay, right? That's part of what being a limit means, right? The limit is L, means we can make them pretty close to L. So let's make them this close to L. Okay. Well, if that happens, then right, AK over BK is between L over 2 and 3L over 2. Right? For K bigger than N, this happens, right? Okay, but then L over 2 BK is less than AK is less than 3L over 2 BK. Okay. But then what you have is that exactly. If BK converges, AK converges. If AK converges, BK converges. Right? Right? So BK converges implies AK converges by the comparison test, right? By comparison test, BK converges implies AK converges, right? AK converges implies BK converges, right? If the bigger guy converges, if the sum of the bigger guys converge, then the sum of the smaller guys converge. If the sum of the bigger guy converges, the sum of the smaller guy converges. Okay. So the comparison test plus this limit give you the limit comparison test. Okay. If this limit exists and is some number bigger than 0, then the two convergences are equivalent. Okay, so that's the limit comparison test. Okay, so let's wait. What's up? Anybody confused? Hey. Yeah. So this converges if and only if this converges. Well, this diverges, so this diverges. Yeah. So wait, the theorem says this will converge if and only if this converges. Well, this diverges, so we know this diverges. Okay. Okay. So, okay, let me ask you to do some examples, do some exercises. So the first one is, say, summation 2k plus 5 over 5k cubed plus 3k squared. K equals 1 to infinity. Okay. Okay, so take 1 minute and find something to compare against that will be easier to figure out its convergence. For which it'll be easier to figure out its convergence. Okay, turn to somebody nearby and say, I compared it against what? Okay, what do you compare against? What's the answer? What do you compare against? Five k plus 3. Five k plus 3 over 5k cubed plus 3k squared. Right. Is that what you compared against? Okay. Why do you? Oh, I see. Because because it's 1 over k,
Right.
1 over k squared. Yeah. So let's say comparing against compare against 1 over k squared. Right? And that's your intuition, right? You think, well, this top is basically like k, and the bottom is basically like k cubed. So this thing is going to converge if and only if 1 over k squared converges. 1 over k squared, the sum of that does converge, so I know that this is going to converge. Okay, right? So you compare. You say, okay, let's look at 2k plus 5 over 5k cubed plus 3k squared over 1 over k squared. right? That is 2k cubed plus 5k squared over 5k cubed plus 3k squared, right? And that, converges to 2 over 5. Right. That converges to 2 over 5, so you know that. So the above converges since summation 1 over k converges, k squared converges. Right? Is that anyone confused? I'm seeing you. Is it confusing? No? Why is this 2 over 5? Well, right, if you take the limit of 2k cubed plus 5k squared over 5k cubed plus 3k squared, you could say divide top and bottom by k cubed. This k goes to infinity. Right? You're going to get 2 plus 5 over k over 5 plus 3 over k, which goes to 2 over 5. Right. Do you see that? Yeah. Right. So this is a typical trick. If you have a rational function, then you divide the top and bottom by the highest power. You say, look, the highest power is k cubed, so I'm going to divide the top and bottom by k cubed, right? I get 2/5 plus things that vanish. I get 2 plus something that vanishes, and 5 plus something that vanishes. Okay. Another one along the same lines. Summation 1 over the square root of 2k, k plus 1. Okay, I just, just tell me, what are you going to compare against? What are you going to compare against? One over k, right? 1 over k or 1 over root 2 times k. I just say 1 over k, right? Right. If you're thinking about convergence, you don't really care about the constant 2, right? The 2 is not gonna change anything, right? If I take out the 2 or put in the 2, it doesn't matter, right? And then this plus 1 isn't gonna matter. I've got k squared, this root of k squared on the bottom. The root of k squared is k, right? So I'm gonna compare versus 1 over k, right? And you'll see that you get some number, and so this thing diverges. Okay, right? And to just make it clear that it works, you say, okay, I have this 1. I have this, and I look at the ratio. As k goes to infinity, I look at the ratio of this, right? This is the limit of k over the square root of 2k squared plus 2k. Right? And then I divide top and bottom by k. I get k over k. Down here, I get the square root of 2k squared plus 2k over k squared. Right? Because because I divide the bottom by k also. Right. So I get the limit of 1 over, as k goes to infinity, the square root of 2 plus 2 over k. Well, that's a constant. That's a positive constant. Any questions about that one? I think the only thing that's a little funny is when you divide by k. Sometimes people get confused by this, right? But you're dividing this by k. That's the same thing as this over k squared, right? Why is what? Why it diverges? Well, because this thing diverges, right? Summation 1 over k diverges, right? Right? You do the limit comparison. The limit comparison says that this thing will converge if and only if this thing converges. But this thing diverges, so this thing also diverges. Right? This diverges, right? Sum over 1 over k diverges. This diverges. And we just compared them and we got a number. We got a positive number. So limit comparison test says if this diverges, this diverges. If this converges, this converges. Why what? Why do we get 1 over root 2? So remember what you have to do, right? You have one series and you have another series. Okay. If, and these are all positive, if the limit of a sub n over b sub n, as n goes to infinity, equals some number, and that number is bigger than 0, then this one converges if and only if the other one converges. This one diverges if and only if the other one diverges, right? That's the limit comparison test, okay? So we compare this with this, right? We compare this guy with this guy, and we see that we get a positive number, right? We got a positive number, so we know that these guys converge and diverge together. We already know that this guy diverges. This is the harmonic series. We already know this one diverges, so that tells us that this one diverges. Last one is a funny one. Summation sine of pi over k, as k goes from 1 to infinity. Okay. So I only give you half a minute to figure out this one. What are you going to compare against? What are you going to compare it to? Did anyone get it? What do you compare it to? Chuck, what's that?
Tangent?
Tangent?
Because then it would be like cosine. Because you got cancel the sign, become cosine. Cosine between 0 and 1, so
Oh. Oh, okay, okay, okay. So you're saying, let's see. So you're saying sine and compare against tangent, right? So that's going to be cosine, right? And then cosine, as k goes to infinity, you're going to get cosine of 0, which is 1, right? And so this is going to converge if and only if the tangent converges, right? Yeah. Okay. So that works. Certainly, this would be comparable. But does this help? This doesn't. Yeah. I don't see how to check if this is made.